Hi everyone, I'm Lei Gao, a PhD student from University College London. Today I would like to present our paper called DataLev, Mid-Air Data Physicalization using Acoustic Levitation. My co-authors are Pourang Irani, Sriram Subramanian, Gowdham Prabhakar, Diego Martinez Plasencia, and Ryuji Hirayama. First, let me introduce the background of this paper. Data physicalization is a technique that encodes data through the geometric and material properties of artifacts, allowing us to engage with data in a more immersive, tangible, and multisensory way. In the last 10 years, shape-changing displays and swarm robots have enabled reconfigurable physicalizations, which can change the positions and the shapes of tangible objects to present charts, such as bar charts, line charts, and scatter plots. However, reconfigurability is still limited in some dimensions, and 3D free manipulation is still challenging. Physicalization materials can be categorized into two types. One type is non-electronic materials, such as food, liquids, and fabrication materials, which are static, but designers are free to choose any materials to present data in a novel way. The other type is electronic materials, such as robots, swarm robots, and drones, which are driven by actuators to dynamically reconfigure the data presentation. However, electronic materials are tightly coupled with their reconfigurability, with the loss of material choices. There's no such a platform that provides rich choice of materials, while also enables good reconfigurability and transformations. Therefore, we are looking into another physicalization technique, Acoustophoresis, also known as acoustic levitation. It allows for the levitation of objects through ultrasonic standing waves. Droplets can be levitated for Gaussian sensation, and light polystyrene particles can be levitated for display. Acoustophoresis also allows for the free manipulation of multiple objects in 3D space, providing flexible control. The next important milestone is using acoustophoresis to create multimodal volumetric displays, which can move levitated objects fast enough to render the POV visual content. Also, haptic and auditory content can be delivered at the same time using the same principle. The latest approach can even enable levitation with sound scattering objects inside the ultrasound field. In this paper, we propose a design space and platform to support building novel physicalizations using acoustic levitation with enriched materiality, multimodal interactions, and mixed reality animations. Our DataLev design space has 5 dimensions: embodiments, materials, multimodal support, mixed reality components, and animations. First, in the embodiments dimension, we consider different transducer board arrangements that provide different levitation space and capabilities. In addition to that, we consider traditional embodiments of physicalizations, such as including static objects in the levitation space, or even adding mechanical devices for dynamic installations. For materials, designers can consider general materials with structures such as particles, threads, and fabrics to build common physical charts. In theory, all types of materials can be levitated in DataLev. Therefore, designers can choose any raw materials, such as food or liquids, that naturally connect with the data context for situational presentations. For multimodal support, the Acoustophoresis system can inherently support visual, haptic, and auditory content, all at the same time. Through enriched materiality, smell-infused materials and edible materials can also deliver data through olfactory and gustatory sensations. For mixed reality components, we propose presenting both digital and physical contents co-located inside the working volume. Here, real MR components refer to the appearance changes of physical embodiments, and virtual MR components refer to immersive and reconfigurable display without using tangible materials. Levitated MR components bridge the reality and virtual reality continuum, which can change the appearance of levitated contents containing both tangible and expressive displays. For animation, we would like this dimension not only to characterize spatial reconfigurability, but also emphasize timing and the relevant principles in animation that can deliver information. Designers can customize their animations or use planning strategies to generate automatic animations. Here we demonstrate some physicalization examples using our design space to achieve mixed reality animation. In this example, we show the bird migration routes use both real MR and levitated MR components, with a particle rendering the POV shape to resemble the bird. In another example, we use similar real MR components and generate automatic animation passes for multiple particles to show the airport connection network. This scientific visualization uses a single-sided transducer arrangement. We include a static object as our dataset and the animated fabric showing the cross-sections of the human head. We also demonstrate this example using the V-shaped transducer arrangement to fit different scenarios. These examples emphasize the multimodal interaction capabilities. In this scatter plot, we use 9 particles to present investment data in different countries over different years. We allow the gesture control and touch to interact with the plots with functions like filtering, sorting, and updating.
Liverpool, Glasgow, Edinburgh.
In this weather report, we include audible sound generated by our system. The virtual MR component is an area image of a map showing the data context. We use a finger to directly interact with the levitated content. To show the heart rate data, we show the heart-shaped POV image as a data context, while haptic feedback contains frequency and intensity to simulate the real heartbeats. Lastly, we show the capabilities of physicalizing different materials. In this plot, we levitate 5 types of real food at their data points. Users can taste and animate different data materials. In this map chart, we levitate real liquid droplets and dynamically change their droplet states when updating the map charts. For different embodiments and multimodal displays, we use the OpenMPD solver to generate acoustic traps at our target positions. We modulated the amplitudes to fit for different materials, haptic and auditory contents. We use the projection mapping to demonstrate the real MR and levitated MR components, and use the area imaging plate to create virtual MR components without wearing any headsets. To achieve our reconfigurable animation, we integrated path planning algorithms in our platform to compute feasible passes and timing without object collisions. DataLev provides many opportunities for future physicalizations. It is possible for designers to create complex charts and deliver rich information. With versatile embodiment designs, they can suit in room-scale setups as well as smaller handheld or tabletop setups. DataLev provides a natural mixed reality display that integrates virtual and physical elements for reconfigurable and expressive tangible display. Also, Acoustic Levitation allows for contactless 3D printing and fabrication. One promising point is to convert dynamic physicalizations into permanent ones, and bridging physicalization and fabrication. Currently, we still face challenges in balancing flexible reconfigurations with freehand manipulation. Although we provide general design space here, more detailed principles for complex physicalizations are unexplored. DataLev still needs further development to become a mature end-to-end platform and needs more feedback from users. Thanks for your listening. For more details, please read our paper.